Hi guys, welcome to this page of the notes, and now we're finally here. After going through all of section 3 and a whole bunch of stuff here in section 4, we have finally come to it, graphing a rational expression, and we're going to do it by finding a bunch of little pieces, putting those pieces together and trying to get a picture, right? Put together the puzzle based on the pieces that we have. This is the rational function I want you to graph, and before we get started on it, there's no point in kind of disguising it or hiding it or lying to you about it. This one's tricky, all right? But if you're taking this class with me, this is exactly the kind of rational function you will be expected to be able to graph, whether on a quiz or on a test. Yes, it's hard, but that's why we practice, all right? I have a ton of example problems that we'll go through together. You will get plenty of practice in the homework as well, and sort of hopefully what will sort of help you through these, as they are, because they are difficult problems, is there's a process, right? We do the exact same things over and over and over. You know, it's just what you get from the process changes depending on the problem. So there's no sugarcoating it. This one's really tricky. Yes, you will be expected to do problems just like this on a quiz or a test. It takes practice, so please practice as much as you can. I will give you a certain number of homework problems. That doesn't mean that's all you're allowed to do. Do as many of these as you need to do to get good at them. There's going to be quite a few of these. Again, if you're taking this class with me, there's going to be quite a few of these on your test. You need to be able to do them. So here we go. Let's jump into it. As always, it's a free response question, which means it is your work that's worth points, not necessarily your final answer. If you throw this in a graphing calculator and then just sketch it out on the coordinate plane I've given you, you're not going to get any credit. I need to see the work. And I've given you a roadmap, right? So here it is. I want the X-intercepts, the vertical asymptotes, horizontal asymptotes, if they exist. If they don't, give me the slanted asymptote. And now in addition to that, find the points of discontinuity, if there are any. All right, here we go. Let's jump into it. X-intercepts first. That means I need to set the numerator equal to 0. All right, so my numerator is, if you take a look at the function above, it is an x squared plus 4x plus 6. All right, here we go. It is a general trinomial, hopefully one that factors easily. Let's find out. I need two numbers that multiply to 6 and sum to 4. Take a second and think about it. Oh man. Okay, let's take a little bit longer and think about it because it doesn't appear to be simple. Oh man. Shoot. Turns out there aren't integers. There are no integers that multiply to a positive 6 and sum to a positive 4. So factoring it as a general trinomial is not possible. All right, this tells me two things. Since it will not factor into two binomials easily, right? It won't factor into two binomials with integers. That tells me that my x-intercepts are either decimals, which is totally possible. In fact, it is more likely that the x-intercepts would be decimals than integers, since there are infinitely more decimals than integers. So that could absolutely be the case. Maybe my x-intercepts are decimals. Could be. Or, if you remember back to chapter 4, this is a quadratic. And sometimes when factoring a quadratic, the quadratic didn't cross the x-axis, in which case we wound up with imaginary zeros. Imaginary zeros just simply meaning it doesn't cross the x-axis. So at this point, because I cannot easily factor into two binomials, I know it's one of two things. Either my x-intercepts are decimals, or I don't have any. They're imaginary. But I still need to figure that out, right? If I have x-intercepts, you need to find them. So how do I do it? Well, again, you've got two options. We go back to chapter 4, Section 5. Chapter 4, Section 5, we learned a method of factoring known as completing the square. You could factor this quadratic by completing the square and find either your decimal x-intercepts or your imaginary x-intercepts. Your second option is Chapter 4, Section 6. We learned a method of factoring using the quadratic formula. Again, the quadratic formula will either give you the decimal intercepts or let you know that they're imaginary. I prefer the quadratic formula, so that's the one I'm going to use. Here we go, right down here. I'm going to need some space for some work because we have to use the quadratic formula. And here's the quadratic formula. X is equal to negative b over 2a plus or minus b squared minus 4ac. You take the square root of all of that, all over 2a. All right, let's plug and chug. Remember, my function was x squared plus 4x plus 6. Right? That means that my a, right, is actually here. Let me write that out for you. It's the general form, right, is ax squared plus bx plus c is equal to 0, right? That's the general form for a quadratic. My quadratic, the one I'm factoring, is x squared plus 4x plus 6. So what that tells me is that a is 1, b is 4, and c is 6. All right, guys. At this point, one of the reasons I like the quadratic formula as the option I'm going to choose is it's plug and chug. Plug in the numbers, don't fat finger something on your calculator, you should be good to go. All right, so it's going to be a minus 4 over 2 plus or minus negative 4 squared minus 4 times 1 times 6 all over 2. That's going to work itself out to negative 4 divided by 2, of course, is going to be a negative 2 plus or minus. You take care of all of this stuff up in here. That's going to be a 16. And that's going to be a negative 24. That leaves you with the square root of a minus 8. And we now have our answer. We know what's going to happen. Right, guys, you remember, hopefully you should remember from Chapter 4, you take the square root of a negative number, and what do you wind up with? You wind up with imaginary numbers. So let's go ahead and find them, right, because I asked you to find the x-intercepts, so you got to find them for me. Here we go. X is equal to negative 2 plus or minus. That negative is going to come out, the square root of negative number is going to come out as an I. We represent imaginary numbers with the I. But the 8 can be broken up into a 4 and a 2, so I'll have the square root of 4 times 2i all over 2. X is equal to minus 2 plus or minus. The square root of 4 is 2, so 2 square roots of 2i over 2. The 2's will cancel, and I wind up with x is equal to negative 2 plus or minus the square root of 2i. All right, those are my x-intercepts. They are imaginary numbers, which means on my graph, when I graph the function, I will not cross the x-axis. They're imaginary zeros. So here we go, right up here. I now know that my zeros are imaginary. They are going to be at x equals negative 2 plus or minus the square root of 2i. They're imaginary. I don't have x-intercepts. Okay, next. I told you this one was tricky. Vertical asymptotes. Maybe that'll be easier. Vertical asymptotes are when you set the denominator equal to 0, and my denominator is a 2x minus 1. Okay, let's see what happens. 2x is equal to 1, x is equal to... All right, that's not so bad. So I have a vertical asymptote at x equals 1/2. Okay, that's not so bad. That was a little easier. All right, horizontal asymptote. Well, remember the way this works? 3 rules. And to figure out which rule it is, you need to know the degree of the top and the degree of the bottom. So let's do that. What is the degree of the top? Well, the degree of the top, the biggest power is an x squared, so that means the degree is 2. In the bottom, the biggest power is an x to the first, so the degree is 1. That means that ax is greater than bx. Guys, this is rule number 1, which means no horizontal asymptote. What does that mean? that means you have a slanted asymptote. And as promised, when I talked about slanted asymptotes on the previous page of notes, I told you I'd show you how to do it. I would remind you of the long or synthetic division when we got to the example problem. And here it is. I don't have a horizontal asymptote. I have a slanted asymptote, and we will need to do long or synthetic division in order to find that slanted asymptote. Okay, let's do that. So, find myself a little bit of space. Hold up. I got myself all kinds of messed up here. Let's see, how can I do this? Let's do... There we go. All right, find myself some space. Oh. Here, got some space right up here. All right, there we go. I got everything dragging together. Okay, so this is my rational expression. Okay, I need to do long or synthetic division. First, when can you do synthetic division? Remember, synthetic division only works. The only way you can do synthetic division is if the leading coefficient in the denominator is a 1. And it is not. I have a leading coefficient of 2, which means synthetic is out. I must do long division. The second thing that you have to remember when it comes to long and synthetic division is if you're missing a power of x. The powers of x must be in descending order, and if you're missing any powers, you must put in a placeholder. That way everything lines up nice and neat in our long division and you don't get lost or confused. X squared, x to the first, x to the 0. I have everybody. I don't need any placeholders in this case. All right, let's go ahead and set it up. I'm going to have 2x minus 1. That's my divisor. My dividend is the numerator, x squared plus 4x plus 6. Use my long division symbol, and here we go. Remember, it's a 4-step process. Step 1, divide, multiply, subtract, bring down. So step number 1, divide. X squared divided by 2x. I like to do that as a little bit of side work. X squared divided by 2x means that I'm left with I'm left with x over 2, or that's the same as 1/2 x. So 1/2 x, and make sure you line up the powers, right? It's an x to the first, so put it over top of the x to the first. Step 1 was divide, step 2 is multiply. 1/2 x times 2x, well, the 2's are going to cancel and leave me with an x squared. Then 1/2 x times a negative 1 is going to be minus 1/2 x. Step number 3, right? So we divided, that's step 1. We multiplied, that was step 2. Step number 3 is to subtract. Don't forget to put it in parentheses because you'll need to distribute the minus sign. That means this is now a negative x squared. This is now a positive 1/2 x. X squared minus x squared, those guys cancel each other out. And then I have 4x plus 1/2 x. Well, that's 4/2 x. Or 9/2 as a fraction. So 9/2 x, and then we bring down. All right, step number 4 was bring down. After step 4, you repeat. So that means that I will now have 9/2 x divided by 2x. All right, good news, x's cancel. The x's cancel each other out. The 2 gets dropped into the bottom, right? That's how the complex fraction works. That denominator goes into the denominator. That'll give me 9 over 2 times 2, which is 4, or 9/4. So I get 9/4. That's a constant. Make sure you put the constant over top of the constant. So plus 9/4. And we get to stop. This is great news. You don't have to complete the synthetic division, and here's the reason why. I mentioned it on the previous page. Please notice I have nothing else to bring down, right? I brought down the 6. That was the last number left to bring down. That means if I do the multiplication and then I do the subtraction, what I'll get is the remainder. But I told you when you do the slanted asymptote, we want the quotient ignoring the remainder. The remainder doesn't matter. So as soon as you bring down that last value, you get to stop. right? Bring down that last value, figure out what that last term in the quotient is, and then quit, right? Because if you kept going, you'd find the remainder, but the remainder doesn't matter. You did work that you didn't need to do, and this guy is your slanted asymptote. So y equals is my slanted asymptote. So we come up here, and right there, actually here, let me put it, I'll just write it right here. My slanted asymptote, my oblique asymptote is at y equals 1/2 x plus 9/4. Let me write that as a decimal. The 1/2, that's easy because that's my slope, right? That's another great point. This is in slope-intercept form. Y equals mx plus b, right? Y-intercept, slope. So 1/2, it's a rise of 1/2 x, and then 9/4 as a decimal. I put it in my calculator, I get 2.25. All right, now the last thing I need to do, right, is just check and see, do I have any point discontinuity? Well, remember, point discontinuity will be if I get the same value in the x-intercept as I get in the vertical asymptotes. My x-intercepts were imaginary numbers. My vertical asymptote was 1/2. Those are not the same values, and so point discontinuity, well, there is none. No point discontinuity, no holes in the graph. All right, guys, here we go. We're going to go ahead, take all the pieces we just found, graph them out, and then go from there. All right, here we go. Oop, 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 oop. Slide all that out of the way. Get my graph. There it is. Okay, so first, I had a vertical asymptote. My vertical asymptote was at 1/2. So I'll put my vertical asymptote in at 1/2. That's going to be right through here. Vertical asymptote was at x equals 1/2. Perfect. Next, I need my slanted asymptote. My y-intercept is 2.25. 2.25. That'll be somewhere right about there. Again, you're freehanding this. It doesn't have to be perfect. The slope is 1/2. Up 1/2. Up 1/2. Right about there. I could go down 1 and back 2. Right about there. Put in as many points as you need to, but your slanted asymptote's going to run right through there and right through there. All right, remember, we do not cross the x-axis. My x-intercepts are imaginary numbers. I don't have x-intercepts. So what you need to be able to do is you need to be able to sketch the function based on what we know the reciprocal function looks like from the previous section. I need to come really close to my asymptotes. I can't touch them, but they get really close, and I cannot cross the x-axis. Well, guys, yeah, it's a little bit of a puzzle, but it's one that's not too difficult. Please notice this. If I were to come this direction along this asymptote to this asymptote, look what happens. I cross the x-axis. That is not okay. I have imaginary x-intercepts. I can't cross the x-axis, which means I have no choice. I have to come this direction without crossing the x-axis. Right? It's the only way to approach those asymptotes without crossing the x-axis. Now, since the graph goes in that direction, it has to come from the opposite side. Since it's going to negative infinity, up here on the other side, it's got to come from positive infinity. And please notice, without touching asymptotes, I do not cross the x-axis. And so there we go. Based on all the pieces of the puzzle I found, no x-intercepts. Where's my vertical asymptote? Where's my horizontal asymptote? Is there any point discontinuity? I put all those pieces together on the graph and figure out how to get my function to fit those pieces. Guys, I know this is not easy. That is a really tricky problem. We'll do many more examples together until you get the hang of it, but I love these things. So head on over to the next page of the notes. I'll meet you there, and we'll do some more graphing.